Hi, I'm Leonard here. And now let's continue to the page 2. In this project, we applied several data mining techniques to analyze the accidental drugs-related death dataset from Connecticut between 2012 and 2023. The dataset contains 11,981 records, and each record represents one family case. The original datasets included 48 attributes such as age, sex, race, location, and substances detected in the toxicology report. Before applying the data mining techniques, we performed several data processing steps. Attributes with more than 85% missing values were removed, and the dataset was reduced to 32 meaningful variables. We also performed feature engineering. For example, we create an age bound variable to group ages into categories, and a total drugs variable to count the number of substances detected in each case. Temporal features such as year and month were also extracted. After preprocessing, we applied 4 main data mining tasks: classification, prediction, clustering, and anomaly detection. Each method helps us understand different aspects of the datasets and provide valuable insights into the overdose crisis. Hi, I'm Leonard here, and now let's continue to the page 3. The first task in our analysis is classification. The goal of this task is to predict whether fentanyl was present in the toxicology report of a fatality case. To build this model, we used several demographic features as input variables. These include age, sex, age bound, location, year, and month. These features represent demographics and temporal characteristics of each case. Importantly, we did not include other drug indicators in this model. This decision was made to prevent data leakage because those variables are measured in the same toxicology report as fentanyl. The model we selected was the random forest classifier. Random forest is an ensemble learning method that builds any decision trees and combines their predictions. This approach has several advantages. First, it can capture complex relationships between variables. Second, it reduces the risk of overfitting. Third, it provides future importance scores that help us understand which variables are most influential in the prediction. Hi, I'm Leonard here. Now let's continue to the page 4. This slide shows a simplified version of the Python code used to implement the classification model. First, we define the feature set that includes age, sex, age bound, location, year, and month. The target variable is the fentanyl flag, which indicates whether fentanyl was detected. Next, we create the random forest model with specific parameters. The model uses 200 decision trees, and the maximum depth of each tree is limited to 12 to prevent overfitting. We also set the minimum number of samples per leaf node to 5, which helps ensure that the model generalizes well to new data. The dataset was then split into training and testing sets using an 80 to 20 radius. Stratified sampling was used to maintain the class distribution of Fantini cases. Finally, we trained the model and evaluated its performance using cross validation and several evaluation metrics.
Hello everyone, my name is Wang Zhengxi. Now I will explain the second data main task in our project, which is prediction. The goal of this task is to predict the number of overdose dice each month. Instead of predicting a category like yes or no, prediction focus on guessing number. In this case, we want to predict how many deaths may happen in critical months. To build this model, we first changed the dataset into a time-based format. The original dataset contained individual deaths recorded, so it will show one cases. However, from the projection, we need to know the number of deaths in each month. So we group the date by year and month and continue how many cases happened in each month. After this step, we got a time series dataset with 144 data points. These data points show the number of deaths each month from 2012 to 2023. Next, we create a new variable called the time index. The variable simply shows the order of time, starting from 0 and increase every month. The time index helps the model learning the overall change in the data over time. Another important step was including the month variable. Months repeat every year, which means December and January are actually close in time. To show this repeat point correctly, we use sine and cosine function. This math function helps the model understand the corresponding pattern of the months. So after preparing the data, we trained a learning regressing model. Learning regressing is one of the most common prediction model. It works by finding the baseline that shows the relationship between the input variable and the result we want to predict. We choose learning regressing because the historical data shows a closing upward trend from 2012 to around 2021. The number of overdose deaths gradually went up over time. This means a simple regressing model can capture the mean pattern in the data. To test the model, we split the dataset into parts. Data from 2012 to 2022 was used to training the model. The final year, 2023, was used as a test. This helps us see how well the model can predict future data. The prediction model helps us understand the overall trend of the overdose problem and provides useful information that could help government decision makers and health organizations plan their resources better. Now I will explain the result of the classification model. The main goal of this model is to predict whether the fentanyl was part of deathly overdose cases. After training the model and testing it with new data, the model reached a correct rate of about 79.3%. This means the model makes the right prediction of fentanyl in about 4 out of 5 cases. To know if this result is good, we also need to look at the basic level of the dataset. In the dataset, phenthine appear is about 67% of all days. If we simply guess that phenthine is always there, we would alright get about 67% correct rate. However, our model improves the correct rate up to about 79%. It means the model perform about 12 percentage points better than this basic level. This improvement shows the population information can help predict phenthine cases. Besides the correct rate, we also checked another evolution value includes precision recall and the F1 score. Precision, so how many of the cases predict as phenthine were actually right. In our model, the prediction value is about 0.85, which means most of the predicted phenthine cases were right. Recall show how many real phenthine cases the model successfully found. Our model researched a recall value of about 0.89. This means the model can find most phenthine related deaths in the dataset. This is important because missing phenthine cases would reduce how useful the model is in real sensation. Another interesting result come from the feature important noise. The model showed that the air variable is the most important function in the prediction. In fact, it makes up almost half of the total importance in the model. This result makes sense if we look at the history of the drug crisis. Over time, phenthine become more common in overdose deaths. Because of this, the air variable industry shows the timeline of the phenthine crisis. Our factors such as age, sex, and location also help with prediction, but their effects are similar compared to year variable. Overall, the classification model show that population help predict phenthine cases, although they cannot explain the full thing. Next, I will explain the result of the prediction model and the grouping model. First, let's look at the prediction result. During training, the model researched an R-squared value of about 0.886. This means the model explains about 88% of the change in the training data. In other words, the model matched the past data quite well. However, when we tested the model using the data from 2023, the R-squared value became negative. At first, it may look like the model did not work, but after looking at the data more carefully, we found that the problem actually comes from the change in the real-world direction of the data. The overdose problem in cognitive increased slow from many years and reached the highest point around 2021. After that, the number of deaths started to go down. Because the model was trained mostly with the data was going up, it continued predicting the deaths would go up in 2023. As a result, the prediction will higher than the real numbers. So the negative R-squared value does not mean the model has no value. Instead, it shows that the description of the overdose problem changed after 2021. This kind of cases is called a data shift, where the new data become different from the past data used for training. Now let's move to the grouping result. Grouping is a type of learning merge that does not use label data. Instead, this try to find the natural group in data. In our analysis, we tested different member of group from 2 to 9. After checking the result using survival evolution value, we found that the best number of group is 2. These two groups are closely related to whether Fontaine appear in a dataset. One group response cases where Fontaine appear in most dice. This group responds the Fontaine stage of the opening drag problem. The another group responds an air lake case where Fontaine was less common, and that's often include material drag such as herring or alcohol. This results shows that the dataset naturally divides into two historical stages of the drag problem. The grouping result is very interesting because another finds this stretches by itself without being taught about Fontaine or the time order of the data. Overall, this analysis help us understand how Overdubb's case has changed over time and shows the strong influence of Fontaine in recent years.
Hi, my name is Li Xiaoyao, and my job is anomaly detection, report writing, and video demo. Now I will explain the results of the prediction model and the class 13 model. First, let's look at the prediction results. During the training stage, the linear regression model achieved an R-squared value about 0.886. This means the model can explain around 88% of the variation in the historical data. In other words, the model fits the training data quite well. The result shows that there is a strong trend in the historical overdose data. From around 2012 to 2021, the number of overdose deaths generally increased over time. Because of this consistent upward trend, the regression model was able to capture the pattern effectively. However, when we tested the model using the data from year 2023, the R-squared value became negative. At the first glance, a negative R-squared value may look at the model completely failed. But after analyzing the situation more carefully, we realized that the issue was actually related to change in a real-world trend. The overdose crisis in the retrieved is peak around the year 2021. After that year, the number of deaths started to decrease. Since the model was trained using mostly increasing data, it continued predicting the deaths were increasing in 2023. As a result, the model overestimates the number of deaths in the later period. Now let's move on the class 13 results. For the clustering, we use the k-means to find the natural groups in the dataset. Unlike classification, it does use labels. Instead, it groups similar records together based on their failures. Interestingly, these two clusters is very closely to the precedence in the dataset. It just it adjusted the Randy index between the labels, and the flag is about 0.98, which is a very strong similarity. It means that it is discovered two major patterns in the dataset. The other cluster represents easier case when it lacks the most deaths when often involved multiple results. The finding suggests that overdose from a pattern to fentanyl pattern. Next, I will explain the results of anomaly detection analysis. In this part of the project, our goal was to identify unusual cases in the dataset. For this task, we used an algorithm called isolation forest. Isolation forest is specially designed to detect in large datasets. It works randomly, splitting the data and oscillating operations that behave very differently from the majority of the dataset. In our analysis, we set the contamination level to 5%. This means the model assumes that about 5% of the dataset may contain anomalies. After running the model, it definitely 599 records as anomalous case. This represents 5% of the entire dataset. To better understand these cases, we compared them with the normal cases in the dataset. One important difference we found is the number of substances detected in each case. For normal cases, the average number of drugs detected is about 1.85. However, for cases, the average number of drugs is most higher, around 3.06. This suggests that cases often involve more complex drugs. In many cases, such as cocaine and alcohol appear together. This complex may represent unusual or rare pattern of drug use. From a public health perspective, this finding is quite important. Many strategies focus mainly on because it's the most common substances involved in overdrugged deaths. However, our detection results show that some deaths involve multiple drugs at the same time. These cases require different protection strategies or more detailed investigation. Therefore, the detection helps highlight unusual patterns that might otherwise be overlooked in the traditional analysis. Overall, this step adds another layer of the understanding of the dataset and helps to identify complex cases that deserve further attention. Thank you for listening.